Alright, in this lab entitled Moon Jump, you guys are going to be looking at some of the original footage of the Apollo 16 on the moon. So I'm just going to play that for you here by clicking on the play button. And you see that the astronaut is jumping up and down. So on Earth, if we jump up and down, the reason we fall back down is because of our weight. And on the moon, that is the exact same reason. The reason why you jump up and you come back down is because you have weight on the moon as well, because there is gravity on the moon. Gravity, though, is less. So, because it is less, it's 1/6 as much as it is on Earth, that affects the height that you can jump at, and it affects, the speed that the change in speed every instant in time. So what you guys are going to do is you guys are going to use the built-in video analysis tools in Logger Pro to track the motion of this astronaut. The lab first instructs you to set the scale, and to do that you're going to use these video analysis buttons here along the side. There's a button that says set the scale, and you're going to click on it, and then you're going to you're given the height of the astronaut, and so you're going to just click and drag across the height of the astronaut down to where from his head to his feet. And then a pop-up menu pops up, and this is where you set the scale as described by the lab. And what this does is it will change the readings on the axes of your lab to measure in meters instead of in pixels, so that when you actually track the motion of this guy, you'll actually be able to figure out how high he is at every instant in time. The other thing that you're going to do is you're going to track his motion. And the first thing we want to do is we want to fast forward until we get to a point where he is not touching the ground. So we want to definitely be, clear of the ground, and that happens at about 5 seconds. And if you look at the top of the video, this is the 5th frame out of 18 frames. So you want to advance it to the 5th frame, and then you just want to click on Add Point, which is a red dot icon with some arrows on it. So I'm just going to click on that, and then I'm going to choose a point. It doesn't matter what point you choose, but you need to choose the same point. So let's say I'm going to track the motion of the top of the astronaut's head here. So I'm just going to click right there, and I'm just going to click every instant in time. I click, it advances a frame, and I'm just going to reposition it and click exactly where that location has moved to. And I'm just going to take time to do that. I'm going to be real careful about it. If I mess up, I can just clear out just close it out and set the scale again and just reopen everything and just redo it. So it doesn't take very long at all. And I'm just trying really hard to do a good job tracking the motion of the top of that astronaut. All right, notice that on the other side here, you now have a graph. And that graph is graphing his position versus time. And you can't see the top point here because the scale's not quite big enough. You could change the scale if you want to. You could go to graph options if you need to, and you can go to the y-axis over here, and instead of it being 3, you could put like 3.5. And now you can see the whole parabola, right? So this is a quadratic function. So what this is doing is it's tracking the position as a function of time. And the position of the function of the time is given by this equation right here in kinematics. The final position is equal to the initial position plus the initial velocity times time plus a negative 1/2 of gravity or minus 1/2 of gravity t squared. So this is our position as a function of time formula from our kinematics equations. And if I were to do a curve fit for this, I would want that curve fit to be a quadratic equation. So what I'm going to do is I'm just going to come over here to my quick tool buttons, and I'm going to click on curve fit, and I'm going to scroll down until I see quadratic. I'm going to choose that. I'm going to say try fit. I'm going to say okay. And then I'm going to look at the equation it gives me. So notice that in the equation, it says y equals at squared plus bt plus c. So I guess what I really want to stress to you is that this is very similar to that formula that we just looked at, right? Y equals some constant plus some constant times t minus some constant times t squared. And in Logger Pro, it's kind of reversed in the order, but the constant a should relate to half of gravity for that planet, or the moon in this case. The constant b, because it's in front of the t variable, should relate to the initial velocity of the object. And the constant c should be the initial position of the object. Okay. So what this means is that A is negative 0.7682. That should be half of gravity of the moon. B is 1.678. That should be initial velocity of the astronaut when he left the ground. And C should be the initial position of the astronaut at 2.094. So now I've got this equation that is basically the same thing as that kinematics equation. So I've got some information about the astronaut. What I would like you to do is I would like you to make sure that you follow the directions in this lab to a T. And then I would also like you to, I'm going to write this out for you.